Just 1 minute. Yeah, Karunya, tell me, you raise your raised hand. Karunya Kalapatti. Hello? Karunya, are you there in the meeting? Yeah. Okay. Are you able to see my screen?
Yes, sir.
Hello?
Yes, sir.
Okay. Okay. Is it recorded? Is it recording or not? Yeah, recording. Yeah, in the last class we discussed this topic, temporary joints. In the temporary joints, we discussed different types of nuts, bolts, and screws. Right? We discussed different types of nuts, bolts, screws, set screws, cap screws. Right? Those things we discussed in the last class. I mean, bolt uniform strength and locking screws, set screws in different types of set screws, flat point set screw, dark point set screw, and cone point set screw, hanger point set screw. We discussed in the last class. Similarly, we discussed set screw different types. Cap screws. Cap screw different types. We discussed like hexagonal headed cap screws, Clister type cap screw, button type, plot type, and hexagonal socket headed type class. Cap screw we discussed, and different types of fastening we discussed. One is through bolt fastening, right? Screw fastening with the different types. Through bolt screws fastening. Through bolt and tap bolt, right? And stud. Those things we discussed in the last class, and applications of the bolt and nut and the corresponding application of these types of screws. Screw fastening and the cap screw applications and the set screw applications, how it is functioning. Those things we discussed in the last class, and difference between the set screw, difference between the cap screw we discussed. Now, bolt of uniform strength we discussed, and especially bolt uniform strength means very important considerations where, for example, in IC engines, cylinder head. I have shown you in the last class some picture also, right? And the cylinder head, very important consideration, because the bolt and nut, whatever we are using, bolt and nut, it should be absorbed energy and released energy. It should be a resilience property. How to improve, how to maintain the uniform strength in the bolt and the nut, bolt and threaded, sunk area and threaded region. Sunk in the bolt, threaded region and sunk region. In the sunk region and threaded region, how to maintain uniform stress or uniform strength. I mean, we discussed in that by reducing the, reducing the core diameter, sunk diameter, as well as introducing the internal holes in the bolt, sunk region, introducing the internal hole in the sunk region. Okay, so that can be that can be obtained same stress in the sunk region as well as threaded region. That is called bolt of uniform strength. We discussed in the last class. And the locking screw. The locking screw different type we discussed a jam nut. Jam nut, two nuts, one nut is in top nut, bottom nut is bigger thickness, and top nut is small thickness. That nut will be acting as a jam nut. We discussed castle nut, and what we discussed is, yeah, split nut also we discussed, and some lockings with the screw. We discussed those things. We discussed. Now we discuss the, terminology of the screw threads. Terminology of the screw threads. Now we discussed, and we go for this. Then we go for some derivations. Then we do problems today. Okay. Now see here, terminology of screw threads. See, in generally we are using right hand threads. Right hand threads are always used for many applications, but in left hand threads are very limited applications. Okay, based on special application we have to produce the left hand threads, right? But in right hand threads, for example, right hand threads, the thread lines slope upward from left to right. Upward from left to right. In the right hand threads, the thread lines are upward from left to right. Thread lines upward from left to right. Right hand threads. Okay, in the left hand threads, the thread lines are, downward from left to right. Downward from left to right. Okay, now that is right, left hand threads. Now see here, this is the portion, internal thread. This is the block. Inside the block, you may assume that to nut also, no problem. In this block or nut, they create the internal thread. This is the external thread. This is a bolt region. This is the internal thread of nut region or block. Okay. Now, see, this is the what is this terminology we should understand while designing the bolt and nut. This is the major diameter. The diameter between the distance. The diameter is nothing but the distance between the crust to crust from the external thread. Major diameter small d. This is the minor diameter DC, right? Minor diameter DC. Minor diameter DC is nothing but this is the, this is the here, this region, the cylindrical rod diameter. Now, this is the minor diameter. Minor diameter. Okay. Now, based on internal threads, how can I say that major diameter here? Here we are saying crust to crust when we are considering the external thread. Suppose if I am considering the internal threads, then the major diameter is nothing but, root to root. The region of root to root is nothing but our major diameter, capital D. Capital D. See here, the root is sitting here. The root is sitting here. Okay. Minor diameter is nothing but, for example, okay. Just take it. Minor diameter, this is minor diameter. Where it is sitting? This is the root. This is the root. Minor diameter, that is nothing but is DC. Root to root in external thread. Crust to crust, major diameter. Right? Now, I come to the base and internal threads. Internal threads, when you are considering major diameter, capital D is, and here root to root. Here root is here. Here we can't say crust. This is root. That will give you major diameter for the internal threads. Now, minor diameter, crust to crust. Minor diameter this. Crust to crust will give you this minor diameter. Okay. Now, you already pitch. What is the pitch here? Pitch. I mean, see here, this is, I mean, pitch diameter. Pitch diameter is the pitch diameter is the diameter of an imaginary cylinder, diameter of imaginary cylinder, the surface which would passes through this, the surface which would passes through, which would passes through the threads at a point as to make, at a point as to make with the width of the threads equal to the width of the space, equal to the width of the space. Okay, I mean, this is, I mean, you can say that in between our, I mean, this is a not a, I mean, not close to major diameter, not close to minor diameter. It's in between pitch diameter. Okay, now, I mean, see here, they clearly given even your Bandari book, you can get it clear information. Okay, you go through that. Now, I mean, the pitch diameter also called effective diameter. The DP pitch diameter also called effective diameter. Now, see, this is internal, external thread. This is internal thread. Now I come to this. Some of the other other terminology. Pitch. Pitch is nothing but the distance between two similar points. This point and this point. This is the distance between two similar points is called pitch. Or you may say that pitch between the distance between crest to crest, from one crest to another crest. You can say that pitch. Or you can say that the distance between the root also. Okay. I mean, mostly we are considering only the top, crest to crest. The pitch is nothing but the distance between the one crest to another crest. Okay, that is called pitch. I mean, the pitch is always measured parallel to the axis of the bolt. Axis of the bolt. Now, what is a lead? I mean, each and every terminology we are going, now we are discussing. Lead. I mean, lead is the distance that when the nut moves parallel to the axis. For example, when you insert the nut on this external thread, when the nut turns one turn, the nut, when you are turning the nut to one turn, then how much distance the nut moved on the nut, on the bolt. When you're turning the nut to one turn, then how much distance the nut moved on the bolt, that must be parallel to the axis of the bolt, right? That distance is called a lead. Now, thread angle. Thread angle is the angle is included between the sides of the thread. This is the side. This is the sides of the thread, right? This is the sides of the thread. Sides of the thread. I mean, sides of the thread measured in axial plane. In an axial plane. This is, I mean, the thread angle is considered 60 degree for the isometric thread. Thread angle considered 60 degree for the isometric thread. Okay. Now, I mean, the last one is a tensile stress area. Very, very important. I mean, the tensile stress area, it has been observed during testing of the threaded rod. During the testing of threaded rod. That threaded rod, I mean, and that an unthreaded rod having the diameter equal to the unthreaded rod. I tell you that, I mean, now what we are doing here, the threaded rod we are going to testing. What is the stress? We are finding the stress level. And unthreaded rod, we would like to find out this stress. When we are doing unthreaded rod, the diameter of the unthreaded rod is nothing but dP plus dC divided by 2. This is the diameter of the unthreaded rod. I mean, this is our pitch diameter. This is our minor diameter. It's going to be a mean dia. Okay. This is our unthreaded rod diameter. Now, when we are performing threaded rod testing, that the stress level must be same with the unthreaded rod. While we are performing the unthreaded rod testing, then we have to follow this condition. dP plus dC by 2 diameter, we should follow this unthreaded rod dimension for finding the stress level. Then finally, this stress level must be same. Unthreaded rod, stress value must be same. Okay, must be same. Now, the cross-sectional area of this unthreaded rod. Now we are saying that the cross-sectional area of the unthreaded rod is called cross-sectional area of the unthreaded rod is called the tensile stress area. Tensile stress area. Please, very important. Keep in mind. Now I come to this, whatever we discussed now, major diameter you must know, minor diameter must know, and pitch diameter you must know when we consider both internal thread with respect to internal thread and external thread, right? Then you must know pitch, thread angle, and lead, and last one is, pitch diameter, the last one is a tensile stress area. These are the terminologies mostly we are using for designing the bolt, in designing the threads, internal threads and external threads. Okay. Now I come to these isometric threads. Some of the things we discuss here. These are the, where is that? Somewhere I missed out. Okay. 1 minute. What happened? Here it's deleted. 1 minute, please. Now, this is isometric screw threads. This is isometric screw threads. Very important. See, now we are going little bit in-depth information about the thread design. Okay, internal thread design or external thread design. Now see here, this is internal thread. Which region? This is a sectioned view. This direction sectioned view is internal thread. Because the nut is already engaged. The nut is inserted inside the thread. For example, the nut is now fitted inside the thread. Now, see, this is the internal thread. This is the internal thread. This is external thread. This is external thread. This one is external thread. This is internal thread. Now, see here. Mostly we are using V threads. For most of the application, we are using V threads because V thread is high friction as well as high torque, and less possibility of loosening the two components between nut and bolt. It's a less possibilities loosening the component. And V threads has a higher strength. Higher strength also. V threads can be easily prepared, can be easily made. V threads. Okay, here also the thread angles, 60 degree for isometric thread, as I told you earlier, we should follow. The base of this triangle, now this is the, this is nothing but base of the, internal thread, which one? This is now base of the external thread. External thread, this is nothing but pitch. Right now, now this is the internal thread is sitting. We can consider pitch must be same. Both internal thread and external thread must be same. Now, see here, this is already we discussed on DC, DP. This is the, with respect to internal thread, we are saying DC, capital DC. With respect to internal thread, we are saying the pitch diameter, capital DP. We are saying this is a nominal diameter or major diameter. This is also called nominal diameter or major diameter. This is same. Similarly, also called nominal diameter or major diameter of the external thread. Means small d. This is internal thread. Okay. Now see here. Now, if you made any bolt or nut, suppose it should be a sharp corner, what will happen? The stress concentration will be more. Stress concentration will be more. These are the, see here, when you are preparing the threads, the roots, in the threads, roots and crest either flattened or rounded in our application. Here I am saying, when we are considering external thread, we are saying that crest. when we are considering the internal thread, we are saying this roots, right? I mean, the roots of the threads, roots of the internal thread, roots, I mean, crest of the external threads, it should be flattened or curved. Then only we can avoid the stress concentration while tightening the nut and bolt. I mean, even sharp corners, it will damage our internal threads. Suppose this is very sharp corners, then it may damage our internal threads also. Then if you are using multiple times, very difficult to use multiple times, very difficult to access the thread, the bolt and nut multiple times. Hence, we have to try to reduce the sharp corners by introducing the see here, this is a standard P/8. I mean, see here, the rounded this is the rounded beyond the width P/8. See here, this is rounded width. I mean, this is for external thread. The P/8 is provided for external thread. All right. Now, I mean, now you can easily understand pitch of the circle is nothing but this is the bottom triangle. If you consider this is triangle, in this triangle, this is a bottom side, is a pitch, right? Now, where the pitch by 2 distance, where this pitch by 2 is available, corresponding diameter, we can say that pitch diameter of the nut, pitch diameter. So now you can clearly understand here. Now this is here, you see here, this where the distance P/2, pitch by 2, corresponding diameter we have to consider, that is nothing but our pitch diameter of the internal thread, pitch diameter of the external thread. Now see here, this region is called pitch diameter now. Okay. Now it reduces stress concentration when you introduce flattened, means rounded arc. It reduces it increases the tool life. Obviously, it will increase the tool life. Also, as I told you that the damaging can be avoided while using flattened and rounded arc. And this kind of arrangement, it will be provide the leakage. Prevents the leakage. It will be prevents the leakage also. And now, I mean, this is the threads. I mean, the threads we are classifying 2 types. One is coarse series, another one is fine series. I mean, coarse series means the bolt and nut, the thread dimensions are going to be more dimensions. Fine series means the threaded dimensions, the pitch, especially pitch and core diameter, going to be a less small. So we are classifying 2 ways. One is coarse thread and fine thread. Okay. I mean, the threaded profile, 2 cases. I mean, generally both are similar, but the dimensions of the threads are based on dimensions of the threads. We are classifying coarse thread and fine threads. I mean, coarse thread consider only basic series. We can say coarse series threads or basic series threads also, we can call that. Okay. I mean, see, core threads are, I mean, there are different advantages. There are some advantages. Coarse threads, where we are using core threads. Core threads mainly we are using in static load carrying capacity. Core threads. And core threads can be easily prepared, and it can be core threads are easier to cut than fine threads, because fine threads we need very accurate tools. Then only we able to cut the fine thread. Okay, these are the advantages. And core threads are likely to be the seized during tightening. Less possibilities. Core threads are less possible to seize during tightening. Seize means that failure. Less possibilities of failure. Core thread. And coarse thread have more even coarse thread are more even stress distribution. I mean, the stress distribution is better in coarse thread, and uniform stress distribution may be happened in the coarse thread. Okay. Now see here, fine thread. I told you that first coarse series. Now fine series. Fine threads. What is the advantage of fine threads? Fine threads also some advantages. Fine threads is greater strength because the fine threads number of threads will be more. Hence, it will be create the more contact region between the nut and bolt. Hence, it will be more strength. More strength. But fine threads we are always using for fluctuating loads, and fine threads always suitable wherever vibration is possible. It is in that place. Fine thread is much appreciated. It can be better. It can be better to avoid vibration. It can be easily absorbed by the bolt and nut. Okay, so fine threads better in the place of vibration. Fine threads, fine threaded bolt and nuts better in the place of vibration regions. Okay, and fine threads are greater resistance to unscrewing the result of lower helix angle. See here, when we are going for fine threads, the helix angle, whatever the angle going to be, it's going to be small. Here, the helix angle. I'm talking about this helix angle. This one going to be small. Hence, more resistance to unscrewing the result of lower helix angle. Okay, so hence it can be tightly held the components when you are using fine threaded bolts and nuts. Now I come to, that is the coarse thread, fine thread advantages and difference between coarse thread and fine threads. Just now we discussed. Now these are the dimensions we should follow while preparing the threads. Internal threads and external threads. See here, this is the h by 2. This h by 2 is nothing but, this is the, take the asymptotes here. Now this is our, what is this? This is our internal threads, right? This is now our internal thread is sitting here. Because of stress concentration, we would like to avoid the soft region. Hence, we have prepared like flatted region. Then make the asymptotes here. From the internal threads, this region from this distance to this distance. When you are going for external thread, this is now external thread. External thread is here. This is maybe a soft region. Here also flat region is there. See, this is a flat region. Take asymptotes, then going to be given this. Then that is that distance we are considering. Take asymptote. The asymptote is going to come here. Sorry, I did small mistake here. Okay. Now the asymptotes here like this. Like this. This is here. It will come. Now, this region, we should follow the design consideration. When we are following this, designing the internal threads and external threads, we should follow this. This the height is h. Similarly, with respect to flattened region, this is the internal thread curved region. Suppose if we are following curved region, then this is small h. When you are preparing here the curved region, then that is small h. This is h3. Okay, curved region. When you are preparing this soft region, we have to use the asymptotes here. Then we have to use h. Okay, flattened region and curved region. How to prepare the distance? How to prepare these dimensions h and h3? I am telling that. Okay, this is P by I. This is already we discussed. Now, there are different threaded profiles you can see here. This is the soft threads. This thread angles is isometric threads is 60-degree angle. This is the Whitworth V thread. This is Whitworth thread. Here 55-degree angle. See here, this is the height. Whatever we discussed, this height here. 0.64 p. Okay, pitch, and this is our fillet radius for the threads to avoid the stress concentration. Fillet radius, I mean, this is a butter thread. This is the angle we should follow 45 degree. This is a warm thread 29 degree. Warm thread 29 degree. See here. I mean, warm thread 29 degree is nothing but this is a 14.5 degree plus 14.5 degree. If you take this 14.5 degree, this is plus 14.5 degree. Okay. Now this warm thread, you should know. These are the things standard. As a mechanical engineer, we should know warm threads. What is the, I mean, angle, threaded angle, 29 degree. Butter thread, what is the threaded angle? 45 degree. Whitworth thread, what is the threaded angle? 55 degree. Okay. What is the V thread angle? 60 degree. What is the square thread angle? Square. This is a square thread. I mean, so in the square thread, this distance. I mean, this is the this dimension must be same. The pitch dimensions and the thickness of the width going to be same here. No. This is a P by 2. This is a P by 2. This is a P by 2 for square thread. I mean, the finally ASME threads. ASM thread is looks like. I mean, this is trapezoidal section. Okay, ASME threads. So this is very important types of threads. Please keep in mind, you may expect this type of questions in the objectives, even competitive exam. This is now, see here, that's some common, I might have been shown early. And this is internal threads. Now, how this is internal threads. This is internal threads. Internal threads, root to root is our minor diameter when you are considering internal diameter, right? Yes. And the crust to crust, sorry, root to root, internal thread, sorry, root to root, internal thread is root to root. Root to root is our DC. For D, capital D. Root to root. Our crust to crust internal thread gives DC. DC is nothing but minor diameter, or you can say core diameter also. So now I come to this standard specification. This is for fine series. Where is core series? I think I missed out. I will show you here in the book directly. Yeah. See, this is this core series. Give me just a minute here. Where is my pen? Okay, anyway, I tell you here, just now here. View, connect, morning used pen. Yeah, comment, it is in the comment only, can get it. Yeah. Now see here, this is basic series. Basic dimension for the isometric thread, isometric screw threads, core series, basic series. I mean, this is the metric thread. M representing your metric thread M. See, 4 is nothing but our nominal diameter, maximum major diameter. See here, this is major diameter. You can see here, this is the major diameter. This is the standard pitch. We should use 1.5 mm. Okay. This is the pitch diameter. Pitch diameter for internal thread, pitch diameter for external thread, pitch diameter for internal thread. Okay. must be same. For example, M10 I am considering. Major diameter 10, pitch is 1.5 mm, and pitch diameter for internal thread and external thread 9.026 mm. Come to minor diameter, DC. This is in external thread. Capital DC in internal thread. Internal thread is always high, 8.376. Here 8.16. Internal thread. For internal thread, minor diameter 8.376. For external thread, minor diameter is 8.16. So DC, capital DC is greater than always small. I mean, they're greater than always external diameter, external thread DC. Very important. Now, tensile stress area. I mean, this is tensile stress area. It's nothing but dP plus DC divided by 2. Then find out area, pi by 4 d squared. Okay, the d squared is not, d is nothing but dP plus DC by 2. Now this is the tensile stress area. Now you consider any metric thread. Here this is the metric thread 60 for diameter. This is a major diameter or nominal diameter. This is the pitch 6 mm. This is our pitch diameter. Pitch diameter for internal thread and external thread. This is our minor diameter for internal external thread, minor diameter for internal thread, always high. Now this is our tensile test area. This is obtained from the design data book. They might have been gone through thorough studies. Then they declared this data book. Then we have to use directly. Now I come to this fine series. This is a fine series. Fine series. We are referring here itself. This is fine series. This is for our pitch. This is for our nominal diameter or major diameter. Here, this is nominal diameter. This is a pitch already represented here 1.25 mm. This is our pitch diameter of the circle. Pitch diameter of the thread. Pitch diameter of the thread, internal thread and external thread same. Now dP is equal to d small dP. But here DC not equal to small dc. Very important. Okay. Now this is the deep DC, small dc. This is a capital DC for internal threads. This is tensile stress area. You should know. Suppose the problem is given M24. This like this. You should know. This is our pitch. This is our nominal diameter. Based on that, you have to go for the design. Okay. Suppose only given this other parameter, if you need, for example, pitch diameter, then go for corresponding table. You can find out pitch diameter is this. Then corresponding DC and DP, you can get it from the table. This is this tensile stress area to find to test the stress level in the threaded rods and unthreaded rods. What is the stress level? During that time, you have to consider this area. Okay. And now I move to next thing. Stresses in screwed fasteners, stresses due to initial tightening. Okay, now stresses due to external forces, stresses due to combination of the both. Now, see here, stresses due to initial tightening. We are going to discuss these things in the later. Tensile stress due to stretching the bolt. Okay, compressive stress on the threads, shear stress across the threads. Okay, shear stress across the threads. Across the threads means, these are the inclined threads. It may create the shear stress. Compressive stress, when it will happen? When you are tighten the component to component by tightening bolt and nut, then compressive stress is going to be created in the threads. Okay, and the torsional stress induced by the frictional resistance between the thread and engagement. Torsional stress, when you are tightening the bolt and nut, then the torsional stress is going to be induced by the frictional resistance between the thread and engagement. See, this is nothing. These are two plates. Then now here, bolt head is here. This is the bolt head. This nut, right? Here, torsional shear stress creating these regions while tightening the bolt and nut, and after also it will be created torsional stress. Okay, these are the now. Bending stress in the surface under the bolt head. Bending stress, when the bolt length is more, then bending is going to be occur. Bending stress is going to be occur in the surface under the bolt head. Depends on bolt size. Going to be occur. And not preferably preferably for me, not perfectly, sorry, not perfectly normal to the bolt axis. I mean, this is based on that bolt size, as if not perfectly normal to the bolt axis, that may cause us the bending stress in the bolt. Now come to this already we discussed. Now come to the bolted joint in simple analysis. Bolted joint simple analysis. So in this joint, now see here, the bolted joint analysis. See here, the bolted joint subject to tensile force P. When you are tightening this is a force schematic diagram. Then here force is acting downward direction on the head. Here the force is acting upward direction on the bolt. On the nut. Here bolt head. This is on the nut head. Then only the component going to be in equilibrium condition, right? Component going to be in equilibrium condition. Now where is this? I mean, which region is this is the diameter DC is the weakest region. This is the weakest section because the threads are presenting there only. When you are tightening, that region is going to be weakest section. Example, you take one bolt and nut, you 100 times tighten it, lose it, lose it. What will happen? The thread is going to be weakened, right? That's what they are saying. The weakest portion is the DC here. I mean, core mean minor here. This is DC. DC is our this dimension, minor diameter. Okay. And come to this. I mean, this is a normal calculation only. The height of the nut can be defined. See, this is just I read. This is very simple only. It's not difficult one. The height of the nut H can be determined by equating the strength of the bolt in tension with the strength of the shear. I mean, nothing but the shear strength, failure by shear strength equal to failure by tension. If you consider this concept, you will be able to define our height of the nut. This dimension you are able to define. Now, each turn, I mean, the given procedure we have to follow here. So each turn of the thread contact with the supports equal amount of load. Okay, there is no stress concentration in the thread because we already considered. These are the assumptions we are considering. No stress concentration, equal amount of load to be shared in the threads. The first assumption, second assumption, no stress concentration. The yield strength of shear equal to the half of the yield strength of the tension, half of the yield strength of the tension. I mean, we already know that SYT is always SYT. Yeah, SYT divided by 2 is equal to SYS. Yield shear, right? I mean, we have to equate yield strength in tension equal to yield strength in shear. We are going to consider. That's what I told you, that the concept failure by shear is equal to failure by tension. While considering failure by shear, we have to use this concept. Okay. Now come to this. I mean, this is where is the shear region? Where is the load is acting here in this region? See, the strength of the bolt is in tension. Strength of the bolt is in tension. When the tensile load is acting, then this is the P. This normal formula only. P by P is equal to P by, I mean, yes, P by P is equal to pi by 4 DC squared. DC squared into SYT divided by Fs. This is nothing but sigma T. This is nothing but sigma T. These are simple calculation only. Okay. Now come to threads in shear. Threads of the bolt with the sheared area. Shear. Where it is shear? Is shear. I mean, this region is going to be subjected into shear. This region. This region, where it is shear is happening, I draw here. This region. I think you're able to see now. This region going to be shear. Hence, what is this area of this region? Pi DC circumference, right? Pi DC into height. What is the height of the nut? That is going to be shear area. Then shear. Then you apply the shear strength concept. Then this is the P is equal to pi DC H into sigma S. Sigma S is shear strength. Tau. Sorry, tau. Sorry, tau. Then tau is nothing but SYT divided by 2. We are applying the, here we also apply here. Here also we applied the factor of safety. Here we are applying the factor of safety. This is going to be our tau. Okay. Now from this relation, we are able to find out. I mean, equate this equation A and B. Equate the equation A and B. What I told you earlier. I mean, designed by shear strength is equal to designed by tensile strength. Then finally, we are going to find out H is equal to 0.5 DC. Simplify this equation, you are going to get this. I mean, this is the, if DC is equal to 0.8 D, then H is equal to 0.4 D. This may be a design data book from the design data book. Now here, suppose, I mean, suppose for here, the standard, whatever we are preparing our own, some of the threads, internal threads and external threads, we are preparing based on our own or based on special applications, then those kind of dimensions may not be available in the data, in the table, whatever we discussed earlier, table fine series and core series. Then we have to follow this. We have to follow this. H is equal to 0.8 D. We have to follow this. I mean, we have to follow this. DC is equal to D minus 1.22687 P, like this. Now see here. I mean, these are the things. I mean, this is, suppose not our threaded design, our bolt and nut design dimensions are not available because based on our special application, not available those dimensions in the standard table. Then we have to follow this to find out our DC, to find out our DC or D. DC is minor diameter, D is our nominal diameter of the bolt. We have to follow this relation. DC is equal to D minus 1.22687 P. P is nothing but pitch. Okay. Now, see here, since, please go through that after complete the class, please go. Since there are two unknowns on the right hand side, D minus 1.22687 P. I mean, hence it is not possible to find out the solution. Hence we have to use DC is equal to 0.8 D. DC is equal to 0.8 D, what we considered earlier. Then that is from the standard data book. Then we are able to find out D or P, whatever we can find out. Now I come to this simple problem. Then eccentric, an electric motor weighing 10 kilonewton, okay, is lifted by means of the I bolt as shown in figure. This is the figure. The bolt is screwed. The I bolt is screwed. This is a single unit. This is single unit. The I bolt is screwed in the frame of motor. Okay, is screwed in the frame of motor. The I bolt has a core threads, is made of plain carbon steel. I mean 30 C8, so it is 400 Newton per mm square, and factor of safety is given. Determine the size of the bolt. Very simple. Then here they have been explained. Now you can go through this the text. You can understand the I bolt. The I bolt is used for lifting and transporting the heavy machinery on the shop floor. You might have been seen in the crane hooks. The crane hooks they are using for lifting the heavy weights. We are using this I bolt. It consists of ring circular. They have means rings. It consists of ring of circular cross section at the top end, and the threaded portion at the lower end. Just I am saying this design. Threaded portion on the lower end. Upper portion is, I mean, circular ring design. The threaded portion is screwed inside the threaded hole on the top of the surface of the machine, which we want to lift. Okay, the crane The crane hook chain is inserted in the circular ring. The circular ring is called I. The circular ring we are selling I. That when this is along with the threaded portion, we are saying I bolt. We are saying that I bolt. That's all. Okay. Now here permissible tensile stress is given. Permissible tensile stress is given. S Y T. Then simple concepts apply this. I mean sigma T is equal to P by pi by 4 DC square. Then we are able to find out what is DC. Okay. Mean minor diameter of the bolt. This is a minor diameter. What is DC? Now you would like to find out the D. What is D? These are the, D is equal to DC is equal to 0.8 D. Then D is equal to DC. D is equal to 0.8 into DC. 0.8 into DC. Now we would like to find out DC. Sorry, I mistake. D is equal to DC. DC is equal to DC is equal to 0.8 into D. Now we would like to find out the diameter, nominal diameter. This is nothing but nominal diameter. Nominal diameter is 18 mm. Okay, this is standard size. Now you come to the table. I mean, belongs to which notation, which metric notation? We come to table M20. This is 18 mm. The diameter, nominal diameter is 18 mm. Belongs to which notation we can find it out? M10. Okay, here not available. I come to here. 18 mm where it is possible. See here, we can consider this one. Okay. M20. I mean, this is now. Suppose if we want, as I told you that you may think that, sir, earlier you told you can go for this design. I mean, if you want mandatorily, you can go ahead with define your DC or P, whatever. But now you can define your P from the. You can define P, right? Then you. I mean, the dimensions. Suppose where it is close in the table. This is close to M20. This is the dimension whichever we discussed. This close to M20. I have taken M20. We can't go for M16. M16 is not advisable. Then after M16, M18 is not there. M20 is there. Then we can take M20. Okay. Now this is nominal diameter. Now this is another problem. Very simple problem. How many shears here? 2 bolt and nuts are presented in these two thin sheets. Then these are 2 shears subjected. Then 2 shears means what is the shears here? 2 shears are subjected. 2 shears. I mean, two places shears are subjected. Then tau is equal to what? Just I write the formula. You can understand. You try your own. Tau is equal to sigma SYT divided by 2 into Fs. Fs is given 5. Divided by 2 Fs. Okay. Now, I mean, here how many shears are there? Shears, 2 shears. Then shear area is 2. Shear area is equal to 2 into pi by 4 into DC square. D square, nominal diameter square. You take it here. They have given nominal diameter, I think. They didn't give nominal diameter. We are going to find out that only. Here they given SYT given. Then we are able to find out the nominal diameter. Then what is this shear force? Shear force is nothing but, I mean, pi kilonewton is equal to, there is nothing but 2 into pi by 4 DC squared into DC squared only we have to find out. Tau we know. This is a tau. Then find out this diameter going to come 9 mm. 9 mm. Then this is belongs to M10. Diameter going to come 9 mm. This nominal diameter 9 mm. Then this is belongs to M10 bolt and nut in from the table. Now we come to the eccentrically loaded bolted joints in shear. I mean, we are we are using multiple bolt and nuts in the components, not only single bolt and nut in proper orientation, right? That's what we should discuss this. I mean, eccentrically, see, for example, they have given here the in structural connections, a group of bolts and nuts are frequently used. That's what I'm telling that frequently used here. Group of bolts and nuts are frequently used. See this figure. Here one nut is connected. Here, I mean, here bolt and nut is connected. Here bolt and nut is connected. Here bolt and nut is connected. There are 5 bolts and nuts used for in this here used here. I mean that the cross section area A1, A2, A3, A4, A5 like that. But you take this is our application. I mean this is the plate, one plate. This is another plate. This different design is connected, is joined with the help of the multiple nuts, multiple bolt and nuts here. Here we are using one bolt nut, here one bolt nut, here one bolt nut, and another bolt nut like that. Now, see here, when we are using like this, yeah, tell me, ma.
Sorry to interrupt, but I'm afraid that we are crossing the time limit, sir.
What is time now?
9:31.
Okay, I stop. Okay. Yeah, you inform me, but okay. Hello?
Yes, it's fine. Yes, sir.
I mean, I'm always appreciated. You inform me at least 5 minutes before. Just inform me, sir. 5 minutes to complete your lesson. Like
Okay,
that,
sir.
inform me. Yeah,
We'll
please.
do that from next class, sir.
No
For sure.
problem because I'm in the presentation screen. I am unable to see the timing. Okay. Sure. I mean, we try to complete the next class the threaded. Threads. After next class, we are going to have power screws. I mean, I try to complete in the next class threads. There are another two eccentrically loaded bolt and joints in shear. The another one more is there. I mean, eccentrically loaded bolts and nuts in perpendicular axis. I mean that eccentric load perpendicular to the axis of the bolt and nut. There are 2 to 3 cases. These 3 cases we discuss in the next class. Okay. Then we try to complete in the next class tomorrow. Yeah, please, any doubt? Yeah. Yeah, do you have any doubt, please? I come to the chat box. Attendance, please. Roll number 1.